Have you ever imagined a computer that behaves like magic? Welcome to the world of quantum computing, where strange principles of physics bring incredible potential. However, there's a challenge. The more qubits we load into a machine, the harder they're to control reliably. The good news? Scientists are finding innovative solutions. A team has recently demonstrated a fresh method to keep qubits stable. Instead of cramming them all into one device, they're spreading the workload across several small processors. Quantum teleportation is the magic glue that holds these processors together in real time. But what is quantum teleportation? It's not about moving matter across space. Instead, it transfers the unique state of a qubit to another qubit far away. This process uses quantum entanglement combined with classical data transfer. Until now, real-world applications of this have been limited. Recently, however, researchers managed to create a working logic gate between two separate quantum chips just 6 feet apart. This breakthrough hints that clusters of small processors can act as one powerful computer. Let's dive deeper. A qubit is special because it can be both 0 and 1. However, this powerful state is fragile. Outside interference can collapse it. By teleporting a qubit's identity, engineers avoid moving the particle directly, thus maintaining its delicate state. In the latest experiment, a team used network qubits to send and receive signals and circuit qubits to process data. The teleportation connected the network qubits first. This entanglement allowed the circuit qubits to act as if they were on the same chip. You might think that a 6-foot gap is trivial, but it opens exciting possibilities. Designers can now upgrade or repair processors without disassembling large cooling systems. This method shifts the focus from brute force scaling to smarter design. Initial plans for quantum hardware emphasized cramming thousands of qubits together. However, this led to increasing error rates. Distributing processors allows each module to remain small and manageable. Teleportation seamlessly connects operations as needed. This new approach also keeps communication efficient. To create a 2-qubit gate across the network, only one entangled pair and 2 classical bits are needed. Engineers can request many entangled pairs to ensure they process cleanly, preserving precious quantum information. This efficiency could expedite the development of quantum data centers. The Oxford University team, led by physicist Dougal Main, is at the forefront of this breakthrough. Previous quantum teleportation research focused on transferring states between separated systems. Their study, however, uses teleportation to establish interactions between distant systems. Their setup involved entangled ytterbium ions and demonstrated an 86% fidelity match, allowing them to execute a simplified version of Grover's search algorithm with a success rate of 71%. That's quite promising for early experimental hardware. They also successfully executed swap and ISWAP operations, which are essential for more intricate circuits. Their experiments confirm that distance does not necessarily degrade performance. Main emphasized that using photonic links to interconnect modules brings vital flexibility. With this, upgrades or replacements can be made without disturbing the entire system. This flexibility is crucial for creating a sustainable quantum computing architecture. But what does this mean for the future? The success of teleportation over short distances is just the beginning. Research has already seen teleportation over more than 27 miles using fiber optics. Linking regions this way can lay the foundation for a quantum internet. Imaging a vast network where sensors, simulations, and encryption work together across cities or countries. Such a setup will allow chemists to design drugs at the atomic level and create secure communication channels immune to eavesdropping. Looking ahead, hybrid systems combining different technologies, like trapped ions and photonics, could optimize performance thanks to teleportation smoothing differences. Yet, challenges remain. Engineers need to improve qubit fidelity, increase the number of qubits, and streamline entangled pair creation. The Oxford team believes that even a small rise in qubit numbers can boost performance significantly. Industry collaboration is underway to establish interface standards. This will enable labs to connect their systems into shared platforms. Instead of building a massive quantum computer, stitching together smaller ones might be simpler and more effective. The 6-foot leap demonstrates that quantum teleportation is ready to become the backbone of future processors. As we step into this exciting terrain, quantum computing moves from being a mere concept to one that can reshape computing as we know it. Do you want to stay updated on the latest in science and technology? Subscribe to our newsletter for engaging articles and exclusive content. Check out our Earth Snap app, brought to you by Eric Rawls and Earth.com, for more exciting insights.